and it's being recorded, so I'm going to agree to that. So Nick and I go way back, actually, and he asked me, I had known about this OceanHackWeek some time ago. In fact, I recommended to a few people to join, and then I got an email from Nick asking me saying they're interested in including a little bit more R content this year, and he asked me if I would give a tutorial on the R package that I co-develop for doing oceanographic analysis. So that's what I'm going to talk about today. This is kind of a pretty broad overview of what I'll admit is a very big package. Does a lot of different things. There's really no way I can cover it all in a 40 minute time spot. So I'm just going to focus on what I think are the most common tasks that people typically use it for. And then, we'll hopefully leave some time for questions. And if you have any, I am happy to get interrupted. So let's just go from the beginning here. So apparently I'm the first R tutorial. This is a lot of Python stuff going on, which is amazing. I love Python. I'm learning it myself. I should probably be taking part in this a little bit more than I was able to this week, but I also love R for a lot of the same reasons that Python is amazing. And also it's just something that I've become very comfortable using, and I find it has a lot of advantages, especially for data analysis. So from the hub thing, we're going to launch the R Studio instance. I don't know how many of you here are users. That's always an awkward thing to say. But R Studio is kind of the default integrated development environment for R. It really is quite powerful. I recommend that you use it. You can use it obviously through the Jupyter Hub here, but you can also use it on your own computer. It is a really nice environment for working in. That being said, you're gonna, if I hit some weird key combination and I delete my whole notebook while I'm working, you can blame the fact that actually I'm primarily an Emacs user, and so I don't usually work within R Studio exclusively. I use it for a few things, but mostly I develop in a different environment. So I love R Studio. I think you should use it, but I don't. So take that with a bit of grain of salt. So we're going to load up my notebook. So we can do that. If you open up the tutorials directory here from our studio, there's one called OCE. And in here is what's called an RMD, or what's called an R Markdown document. For those of you who aren't used to this sort of thing, what this is basically a combination between a typical Markdown document and something you can put and run R code in. I love Jupyter notebooks. Actually, I use them all the time, even with the R kernel. But there's a nice sort of cleanness to these R Markdown notebooks that I really enjoy. So I'm not going to do like a presentation. I don't have slides. What I have is a document that I'm going to talk about as I kind of go through it. So you can listen to me, or you can read what's on my screen or on your own screen if you're doing your own instance of this. And you can interrupt me with questions, as I said, at any time. But this isn't going to be just a present questions. I'm going to show some text and some images and some examples of how I do things in this. But okay, so just to get started, like Python, R has a packaging system. It's very mature. It was sort of baked into it from the beginning. And with that in mind, many years ago now, my PhD advisor, Dan Kelly, and I started taking a lot of the sort of tools we've been developing for doing oceanographic analysis, and specifically, there's a focus there on working with data, or working with real data, and started putting them into an R package, which makes it easy for other people to use. There's a system in R called CRAN or CRAN, which is the Comprehensive R Archive Network, that distributes those packages. And what the goal was to kind of pull a lot of these tools that we and some other oceanographers were using repeatedly into a consistent framework and a consistent package. And over time, the package has grown and it's evolved to incorporate a lot of different things. And so the beginning here, in my little introduction, I just sort of talk about the philosophy there, but also some of the things that the OCE package is capable of, including, there's a lot of seawater equation of state things, which I'll hopefully show a quick example of. There's extensive support for object metadata, and that includes things like units and scales, but also just typical metadata like you would normally get in a data set. And this is different from, a lot of people think of R is the thing you use when you have CSV files, and CSV files rarely have metadata, but that metadata can be very important for your analysis. It has ways of doing a lot of specialized oceanographic plots, which I will show some examples of. Because many of us oceanographers, physical oceanographers in particular, were migrating towards things like Python and R from MATLAB back in the day. One thing that is included in this package is some better facilities for doing sort of p-color or image type plots. It can do tidal analysis, which is based on similar, at least, to the canonical T-Tide package, which was a MATLAB thing. It makes doing mapping much easier than it used to be able. You used to be able to do it. And some of the recent work we've really done is working with data quality flags. And that, I'm not going to get to that today, but it's actually, I think, really one of the highlights of this package. It allows you to work with data that comes with data quality flags, but also to be able to flag your data and handle that in a way that's sort of within a consistent framework. Just because I know that I'm going to run out of time and I already am not planning on getting through everything, right at the top of this document, I put a bunch of resources that I really encourage you to check out. All right. So the first is that there's an official page on CRAN for the OCE package. I'll talk about this maybe in a minute, but we do development for OCE on GitHub, and then maybe twice a year that package we release a version and that gets uploaded to CRAN. So you can always go there to get the latest supported version, and you can go to the GitHub page, which you can find from the next link here, to look at the development version. So any bug fixes or new additions tend to be in the sort of the development version of OCE. I have a little blog that I, often post about ocean data things. Often OCE is a feature on there. It's not always, but there's quite a few sort of resources on there. And finally, I don't get any royalties from this, so I can advertise it, without a conscience issues. Is my friend Dan Kelly's fantastic Springer book, which came out a couple of years ago, called Oceanographic Analysis with R. Really goes through so many things that the package is capable of doing. And it actually goes beyond that to show some really nice examples of how to use R generally and how to use the package in a research setting. And I was going to put more details in this, but there's one chapter where what Dan does in it is takes 4 canonical papers from the literature. So like the Monk 1966 paper and the Riley 1970 paper, like a lot of these canonical papers in physical, biological, chemical, and geological oceanography. And he redoes the analysis in R, sometimes using things in the OCE package, but mostly just showing how you could reproduce these results from these very classic papers within R and how to do that. And I love that chapter because it's such a nice demonstration of not only how useful R is as a data analysis tool, but also like how genius some of those classic papers really were and how like advanced they were for their time. So check that out for sure. So, the first thing you should always cover is how to install your package. Okay, so as I said, OCE is hosted on CRAN. So it actually means there's a really easy way to install it. And I don't know how many of you are watching me on the screen, but what I will probably do as I'm going through these examples is add some bits in here and whatever. But the nice thing about these R Markdown documents is you can add code chunks in. See if I remember how to do this. Is this going to work? There we go. And you can install .packages OCE. And I'm not going to run this. In fact, I'm going to put any val equals false on that code chunk because I don't want it to run. But this is how you get OCE. It's super easy. You install R, you install RStudio, and you give that command. And depending on your operating system, that should work pretty seamlessly. So certainly for Windows and Mac, that will download a binary version of the package and just install it. If you're on Linux, or if you're trying to install the development version, so this is what I'm talking about down here from the GitHub page, you may need to have more things installed on your system to get that to work. And I won't get into the details of this, but there are quite a few details on the GitHub site about how to install the development version of OCE. The reason it's tricky is because we incorporate a lot of other libraries. So there's some Fortran code that gets compiled to run the geomagnetic model. There's C code and C++ code and other things that need to be built properly with the proper system dependencies in behind it. So, in R, the nice thing, that I would say about R is everything just works. And that's usually true until you get into a package that has a lot of complicated interconnected pieces. And OCE is on the complicated end of trying to build, but it's not impossible. My main work environment is actually a Linux environment, so I'm kind of used to making sure that you have the system libraries that you need installed, and I've got some good guides written on the webpage for how to do that. We use the GitHub page for issues, which can be bugs and questions and feature requests. And I really encourage you, if you find something weird or wrong or that you'd like to see or that you don't understand, to just open an issue there. And we're usually pretty quick to get on those to discuss and give advice. Okay, I don't know, that's a bit of the what is OCE overview. Are there any questions at this point? Probably I haven't really gone into any specifics yet, but if there are, just interrupt me, or the moderator can interrupt me. So here, microphone.
No,
there.
it looks
Nope.
it looks like you're all good.
Okay, good. Thanks, Matt. So just a bit about working in R and the package. So R has a whole bunch of different object orientation systems, and I'm going to kind of assume that most of you know what I mean by that in working with Python packages and different objects. But in R, OCE specifically uses what's called the S4 object orientation system, which it's quite an old system. There certainly are newer ones that exist in R, but what we really like about it is that it is baked into core R, and you don't need any additional packages to be able to use that. And I like to say that it's just magical enough that it always blows my mind how sort of things you can make things just work seamlessly, but it's also kind of a pain in the ass to get it working if you're starting from scratch. So it's one of those things where there's a trade-off between development complexity and the ease of use, right? And the ease of use is quite high of the S4 system, but the development complexity is also quite high. So for people who want to contribute to the package, this is not meant to be a discouragement, but certainly we encourage you to open issues and discuss with us before you do something like submit a whole pull request on a new function, because we want to make sure that it fits into the object orientation system that we're actually using. Another note, because this is a common one in the R world, the R has really changed a lot in the last maybe decade. I'd say it's actually less than a decade though, with a real revolution in terms of what's known as the tidyverse and the ggplot2 graphics engine. And OCE, because it's such an old package, actually it isn't really what I would call a tidyverse compatible package. And it also doesn't, for any of its internal plotting methods, does not use ggplot2. Now, that's partly because the package has existed for longer than those things have been around, but also because me and Dan and the other developers are kind of old, and we actually like using base graphics. I'm not against ggplot. I'm not going to. This isn't a ggplot versus base graphics sort of pitch, but just generally, like most of what the plotting methods in the OCE package are for quick plots. You want to do a data summary, you want to see what you've got. If you want to get into making publication quality things, there's certainly no reason why you can't export the data into whatever form you need to use whatever graphics engine you want. But I will advertise that there is an in-development package by one of my colleagues called GGOCE, which is pretty new. It's only on GitHub right now, but it really makes using ggplot with OCE objects quite a bit easier. So if that's your bag, please try installing that and testing it. It's an easy GitHub install, and you can submit issues and requests and stuff at that GitHub page. So just generally, the sort of philosophy of OCE is that it's built around these so-called objects, right? So, we have objects that have different classes, but within OCE, all objects that are created as a part of OCE inherit from this OCE class. And this is not showing up for some reason. I don't know why. I'm just going to click on if you click on that preview button, you can see the notebook in a separate window. I don't think you're probably seeing that on my screen, so I'm just going to keep it closed. You can look at this on your own, but there's a basic sort of structure to an OCE object, and this is consistent across all objects in OCE read from any kind of data that OCE supports, or things that you create on your own if you want to add new ones to it. But basically, it consists of these three things called slots. Okay, now a slot is a term that comes from the S4 object orientation, but it's just a container. It's just a place to hold stuff. Okay, and so we have three things. We have the data, so that's where you store the actual data. We have the metadata, and this holds obviously metadata, but then we also have this thing called a processing log. And basically what this is a history of the object. So as you use different functions within the OCE package to make changes to your object, to trim it or subset it or change it, many of those functions will actually automatically write entries into that history, into that processing log. So if you're working in OCE and you save an object and you send it to someone else, or if you load up something that you'd been working on years ago, you can have a reminder of the history that created that object without necessarily having the code that created it. Obviously, it's better to be organized and keep the code that created the object, but in the event you don't, there is a history contained in that object. So with that being said, the sort of first thing is, well, how do you get at the stuff that's in the object? Okay, and many of the OCE functions will just use the object as they exist, but there are certainly times where you want to just grab the salinity. You have a CTD profile that you read into OCE. You want to just grab the salinity. And the way to do that, there's a few ways that you can get at it directly using the slot notation, which is this @ symbol here. So we say you have an object called D. We want to go in the data slot and we want to grab the salinity. And so for those who aren't familiar, the $ here represents a list, an R list, and you get at the various named fields using that $. I'll show an example of what this looks like in a minute. But there's an easier way to do that, and it's sort of a more R way, and it's to use this square bracket notation. I don't really know what that's called in R. We call it an accessor. It's the accessor function. It's a way of putting the field that you want to extract from the object. So there's some examples here of, for example, how to get help if you want to look up the details on these things. There's a generic OCE object method, but there are also methods that are specific to the different kinds of objects. So here's how you would find the help page for the CTD method for this accessor function. And how do you use it? Well, it's very easy. It's a lot like accessing any other data frame or object in R. Is you give your object name, bracket, and then in quotes inside you put or as a character, you pass the name of the field that you want to extract. So if salinity is the thing you want, it doesn't matter if it's contained in D @ data $salinity. This will find it and extract it for you, so you can do other analysis outside of the construct of that object.
Hey, Clark.
Yeah.
This is Matt. Is there any way that you could render the actual page so we can see it a little bit more clearly?
Yes. Maybe
increase the font a little bit.
I can increase the font for sure. Yeah. Is that better? I haven't gotten to stuff that are actually, there's not much rendering yet. If I click the preview, you probably don't see that because I'm not sharing that screen. Is that true?
That's correct.
Okay. Maybe what I will do is all right. Let me stop sharing for a second. And what I'm going to do is just share my whole screen so I can flip back and forth where I need to.
Oh, that would be perfect.
Okay, so now you're probably seeing the rendered version of that notebook.
Yeah, that looks much better.
Okay, and this, I haven't gone through to the code bits yet, but this looks a little cleaner. So, and just to go back up, here's that image that was missing of the objects, right? So you have something like a CGD, you've got these slots, data, metadata, and it's called processing log, but it is a history. They will have all the different things in it, you know, so metadata could be file names and headers and ship names and institutions and stuff like that. Right, so this bracket accessor is kind of the all-powerful thing, right? It's how you can get anything out of an object, whether it's some of the data or some of the metadata, or and in some cases, and this is what I go over in this point here, is it actually can also provide derived functions, right? So for those of you who understand seawater properties, you know, we measure temperature, but often when we do an analysis, we don't want to use in situ temperature because it has a dependence on pressure. We want to use something called theta or conservative temperature, and so there are some of these things that are commonly used. So here's an example for theta. We can actually get for a particular object the potential temperature known as theta just by calling it with that double bracket notation, even if it doesn't exist in the object, right? So it's a way of getting derived things as well. Okay, so I thought with that, you know, we're kind of 20 minutes in here. I wanted to just go through some quick examples of how I do this. And maybe I'll just stick with the rendered one because I think this actually has most of the output rendered from when I did this earlier today on the Jupyter Hub. But, you know, for me, and I find based on the GitHub issues, probably 90% of the usage of OCE is related to CTD data. So I'm going to assume that this is OceanHackWeek. Most of you know what a CTD is. I won't get into all the details, but this is, you know, sort of the workhorse of modern oceanography, not just physical oceanography, really all fields. You know, they require knowledge of the salinity and the temperature and the depth, although obviously CTD measures conductivity, but we use that to get salinity. So to do some of these examples, you know, actually we have some data sets built into OCE that are nice for doing examples of this. I encourage you to take some of your own data and follow through this notebook to try and do some of these things on your own data. And I'm happy to field questions at any time after the workshop or any time on that, but I'm going to use one of our built-in data sets. So, you know, this is a classic thing is how you load a package. You use this library command. I'm loading two packages here, OCE and the Magritter package, just because the Magritter package provides what's called a pipe, which is a nice way of piping functions together. I won't get into the details on that, but we might see it in one of my examples. I will point out that OCE depends explicitly on two other packages that it will also load, okay? We might get to some of these. The GSW package is the Gibbs seawater. So this is an implementation of the seawater functions from what's called the thermodynamic equation of state, which was released in 2010. Basically, this is what you're supposed to use for all of your equation of state calculations in oceanography. And it's not necessarily always the one you want to use, but it is the one you're supposed to use, certainly when you're publishing things. I won't get into that debate now, but GSW provides all of those functions. The old ones, the ones that we call UNESCO, are also provided in OCE. So you still have access to all of those as well. You can decide which one you want to use. So the example that I show here, we actually have the file included in the package in OCE. So you can actually load that file directly. And I'm doing it here with this magic system file command that loads the external data from the OCE package. The file is called ctd.cnv. Anyone who's worked with Seabird files before will recognize the CNV extension as a Seabird file. Which we can read into an OCE object using the wonderful read.oce function. Okay, so I encourage you to look at the help for read.oce, but basically what this does is it looks at the file, it tries to figure out what it is and determine whether it's something that is supported by OCE. And if it is, it will call the appropriate read function to read that in. So for CTD data, it will read it into a CTD object. For other things like echo sounders or ADCPs or Argo data or satellite imagery, it will read it into the appropriate object. So typically I always start with read.oce because it can handle 99% of the things that I'm trying to read. You'll see OCE gives a little note actually when I load this file like this, it actually points out to me that the temperature in this thing was measured on the IPTS68 scale, and that's what it stores in the object. But for those of you who are familiar with this, typically, certainly for the GSW functions, most things now really want you to be using the ITS90 scale, and it's a pretty simple conversion. And this warning is given because basically because it lets you know like what's being stored in the object is what was actually in the file. But one of the things that OCE does is it takes care of those units, right? So it will look at the units when you try and do further work with this for equations of states. And if it sees that something's in the IPTS68 scale, when it needs ITS90, it can automatically do those conversions. So, I think this warning, but also this way it handles units is really a demonstration of the power of OCE for data analysis, because there are a lot of things that you can get tripped up on when working with data like this. It can be very complicated, the scales and the units and all of those things. If you don't want to go through all that hassle, you can actually, because of how we've included this, you can load that same object from a stored R object in the package using the R function data, which loads this CTD data set. And I'm just saying here, I often use this as an example because these things are so common in all fields in oceanography, right? So just as an example of the object orientation, R has a function called plot. And plot is what we call a generic function. It will look at the class of the object and it will do the appropriate thing for that type of object. And within OCE, we have plotting methods for OCE objects and for specific kinds of OCE objects, such as CTDs. So you can see this one line, I say plot CTD, gives me a summary 4-panel plot that looks like this. This is the default thing that you get. If you look at the help page for it, which I'm showing you how to do down here, there's a lot of different things you can do with this for looking at different ways of summarizing your data or different things that are inside it. This is the default where it shows you profiles against pressure of the temperature and the salinity. This one is potential density, and n squared is buoyancy frequency, shows you something about stratification. There's a TS plot down here and a map, right? So a lot of these files include the longitude and latitude in the metadata. OCE knows where to find those and can turn that into a map. And this is an example that was taken very close to where I am right now. I'm about here is where I'm sitting. This is Bedford Basin, it's called. It's the main harbor here in Halifax. So just to show you, I show that image above of what a classic OCE object looks like. And if we use the str or the structure command, we can actually look inside the CTD object and you can just see what this actually looks like in practice. So when I look at the structure of this object, we can see it's class CTD, it's from the package OCE, and it has those 3 slots, right? So the first one is metadata, which you can see contains things like the units, right? So here's where these units are kept track of. Each field, scan, time, pressure, depth, temperature, salinity, etc., has what we call a unit and an and a scale, all right? So for example, temperature has the unit of degrees Celsius, and it's on the scale of IPTS68, right? Because a unit isn't always enough, right? Sometimes you need to know the scale. Temperature is a good example of that. Salinity is another good example of that. Salinity, at least practical salinity, and I'm not going to get into the details here, has no unit, right? So the unit thing is empty, but is defined on the PSS 78 scale. If you were using the more recent TOS 10 GSW stuff, these will be different. Salinity actually has a scale, or it has a unit and no scale. But again, let OCE handle that. It has a flag spot, which I'm probably not going to get into. It has a bunch of different, metadata things. So what the pressure type is, what kind of deployment, the water depth. Not all of these are filled in automatically because they're not in the file, but a lot of this metadata is just coming from the file. You can see the data slot here, which is a list that has 7 objects, which we saw from the units. And then there's a processing log. So this only has 2 items in it because all that's really been done on this object is to basically read it in and create the object. I will point out this, if we go back to the metadata, there's this thing called data names original. And this is sort of a recent-ish thing that we added, but this is a way of mapping the names that were in the file. So here's what they were called in the file to the names that we use in OCE, which you can see in the data slot here. We use things like temperature, all lowercase, and salinity and pressure and depth. And so these are actually mapped from these names. And this is done somewhat manually. We have the Seabird manual, so we know what things are supposed to be called what. But it makes it, one of the advantages to doing this is that if you have different objects created from different data files, temperature is always going to be temperature, right? You can do your analysis to pull in temperature from a range of different objects using the same thing. However, if you ever want to get back to that original name because you have some analysis where you need to distinguish them, you can always use that original name within the bracket notation to pull that thing out. And here I'm showing this thing was originally called T068 in the CNV file that we loaded it from. And we can always get it by referencing that original name, even though it wasn't stored in the file with that. OCE knows how to look for that in the original name, so you can use either one. And there's quite a bit of power in that. Okay, so that's reading a file. We've read it in, we've looked at it. What about actually using it? And by using it, often you want to do an analysis, but typically the first step that most people get is that they actually need to do some processing on it. And there's a lot of different things in OCE for working with CTD data, including some of the sort of basic processing steps that you may want to do. And I point out here, like, there's a lot of things you can do to a CTD data. And for Seabird, in particular, files, a lot of that can actually be done within the Seabird software. And depending on the data pipeline, that's probably where that processing is done before it produces a final file. But I like to point out that the Seabird data processing software is not available to any other CTD data, right? It's great for doing Seabird data, but you can't use it for RBR or YSI or AML or OpenCTD. You build your own CTD, you've got to do your own processing. And so, using a system like R is actually a nice way of putting all your different data into the same paradigm to do that. Seabird is also closed source. It's free to get it, but you can't actually look at what it's doing on the inside. And perhaps the bigger thing for me is that it's Windows only. So it's a pain if you work on a Mac or on Linux to actually run that Seabird software on your own. You need to rely on someone who has a Windows computer. So just some of the functions that we use for looking at CTD data. There's this plot profile, which is a nice plotting function I'll show. We have a function called CTD trim, one for finding profiles. This is for extracting multiple up and down casts. And then one called CTD decimate, which is for basically averaging the raw time series data into pressure bins. We usually call those bins. And this is often the last step of a CTD processing chain. And again, read the help pages. There's a lot of information in there. And a lot of arguments and things that you can tweak for your specific cases, right? So just to demonstrate this, I'm going to show one of the example data sets that we have in OCE called CTD raw. And this is actually the raw file that we got out of the CTD instrument before we created the CTD object that I've looked at so far. And we can load that the same way. We just do data CTD raw, and then we plot it, right? And so we get the same 4-panel plot. But if you look at this now, you can see it looks pretty gross, right? Like clearly there's some profile information in there, but there's also a lot of really wacky points, like the pressure or the salinity and the temperature have values that look like they're at 99, which is interesting. 99 is often used as a flag value. And those are throwing off a lot of these plots, right? So there's clearly some issues with this. And one of the ways that we can kind of get a first sense of what our CTD cast looks like is using this function called plot scan, right? So a scan is kind of the terminology that we use for a sample in a CTD file. And what this does is it plots a series of the pressure values in the CTD against the scan numbers, right? So this is just the successive samples of pressure and what they look like. And so when you look at this, you can see something that looks fairly typical. Well, there's some big spike at the beginning. It looks like there was some error with the pressure sensor right when it got turned on, which is not uncommon. It then sat near zero pressure for a while, 150 scans or so. And then the pressure increased sort of linearly until it's tapered off and then decreased again as it came back up to the surface. So we can also look at the time series of temperature and salinity, and I've done that using just our plot command. This is a bit of you'll see how to do this if you look in the help file, but I usually remember. We can control the different plot types with this which argument. So this one happens to be, we can give some numeric arguments for this. This gives us a salinity and a temperature time series. So if you look at this, you can see mostly things actually kind of look okay, but there are some very low salinities at the beginning, right? This is probably when it was in air or close to the surface. There's this spike in both of them. And we want to try and get rid of that stuff without having to manually go in and blank out data, right? So this is where I'm using the pipes in Magritter, but I'll point out that this is the same thing as just wrapping functions within functions, right? So we could start with our CTD raw object, we could put it inside CTD trim, and then we can wrap the whole thing in plot profile. What these pipes are doing is just making it a little bit clearer that we're taking our object, right? I'm piping it into this function CTD trim, and you'll notice, because I put the brackets here, but I haven't put any other arguments. So that means I'm using CTD trim with whatever default arguments it has. And then we're dumping the result of that into this plot profile function. And if we do that, we get something that looks like this, right? So this is that temperature and salinity plot. So temperature's in red, salinity is in green. And you can see that one thing this has done is gotten rid of those 99 points that were in there, but it hasn't really done a good job of trimming out these weird points near the surface, which are very likely because of that surface soak or when the instrument was first turned on. So if we go into CTD trim, right, here's, in R, you look at the help page by just doing question mark times or in front of the function name. We can look for other settings and methods. And I encourage you to look in there. There's a lot of different things you can tweak, but one of them is that there's a method, which we call the SBE method. Okay, this is actually based off of what the Seabird data processing does in their software, which we've implemented in this CTD trim. And it's pretty good, actually, especially for Seabird data, if you follow the sort of standardized procedure of how to do a soak and a profile. And so if I pass that now through CTD trim, but I specify the method equals SBE, and there are other ones, and then I plot that profile, you can see we get something that looks quite a bit better, right? So here's where we've taken that raw data that had some bad points, it had some surface soaks, and we've gotten rid of a lot of that stuff pretty automatically by just using some of the easy methods and the easy defaults in here. And that looks quite a bit better. And you can't really see it in here, but if I scroll back up, actually the original plot we did, you look how these lines actually look a little bit thick. And if I zoomed in on these, the reason for that is because our original data had both the downcast and the upcast, right? So the sensors just stay on the whole time. They sample that down and the up. And we usually want to get rid of that upcast. And that's that's another thing that CTD trim has done, is it's kept only the downcast. You can keep the upcast if you want. Just to show it, so there's a plot TS function, which does this sort of canonical temperature salinity plot, which is a nice way of summarizing CTD casts and data and water masses. But I'll also point out that in R, a very common function that you use is a function called subset. This is similar to plot. This is also a generic function that can be tweaked for specific classes. And we've done that again in OCE. So you can actually subset your data using this subset function based on these sort of logical expressions, right? So if I want to take my CTD object, I want to get all the pressures that are between 10 and 30 decibar, and then I want to add those to my TS plot with a different color. Here I'm using color equals 2, then I can do that, right? So I call plot TS, I call this subset, and then I add that to the plot, and then I call another subset where I subset all the temperatures greater than 10, and I add that to the plot. You can see those different colors here and how that works. This is kind of just a toy example, but just to give you an idea. I see I'm getting close to the end here. So the one thing I'll mention is that, reading in known file formats is nice. OCE is pretty good at that. But you don't always have a file format that's standardized, right? Sometimes somebody gives you a CSV file or a .ctd file or some crazy binary weird thing with CTD, and all that matters is that if you can figure out how to read that data, you can coerce it into a CTD object. And we do that using this as.ctd function, right? So the default is that to create a CTD object, you need to have a salinity, you need to have a temperature, and you need to have a pressure. And you can actually have more stuff than that, right? So here's an example where I'm just making up data here, right? So it's just our norm, and I'm adding some things to it. But I can also use this OCE set data function to add additional fields. And you'll see when I do that, I can add, say, nitrate, right? Here, I'm a chemical oceanographer now. I'm pretending I can add some nitrate, and it's got some unit, micromoles or something. I don't know. I just made that up. I'm not really a chemical oceanographer. And you can set other metadata for this that might be important, right? So this was HMS Bodie McBoatface that collected this profile. And then we can, we can plot it. We can plot the CTD, do a plot profile of just the CTD. We can do it and focus on just the nitrate. And for some reason, that one's not showing up, and I'm not sure why. There might have been an issue with that. I'll fix that before we share. So yeah, the as CTD is a very powerful function for casting things that aren't known file formats into CTD objects. So again, you can keep your analysis consistent across a wide range of instrument types and file types and other things. So I have a bunch of other things still in here, which I encourage you to go on and look at yourself. The seawater functions, I think, is a pretty important one, because if you do any conversions or calculations, you're going to want to use those. I also have a little section about, or a section, pun, about what we call section objects, which are collections of CTD stations. So this is, I think, a really powerful way of showing ocean data, from sequences of CTDs. There's some nice ways of plotting images there. Doing TS plots. And then I listed some other topics here. These are all in the vignettes for OCE, that if you go to the OCE website, you can look at details for this. There's examples, there's exercises, there's all kinds of things there. So I encourage you to check those things out. And yeah, I'll wrap up there, and I'm happy to take any questions or criticisms or hate mail or whatever.
That was fantastic. Thank you, Clark. One of the questions that came in is, what is a vignette?
Oh, okay. Good question. I'm sharing my whole screen, so let's go back up to the top. So in our packages, there's a way of including example documents, much like the one that I've done here. If I click on this, where does it go? Here's the OCE webpage. Okay, this is what we host this on GitHub, but it's also contained in the package. And we have these, there's a get started document, this is included in the package. You can actually look at it right in R. This is a lot of what I just talked about, actually. But we've got other ones here, right? So here's one dedicated to CTD data, acoustic Doppler data, flags, map projections, et cetera, et cetera. So these are all things that are contained in the package itself. When you install that package, you can look at it at the R prompt. I forget exactly how to get back, but anyway, if I go back to my RStudio window, this is the one here, and I bring up my R prompt, you can get at vignettes using the vignette function. I think there's a vignette OCE, and it kind of pulls it up in the help window here, if I expand that, or you can look at them on the website.
Cool, thank you. Felipe, you have your hand up. Can you unmute?
Yeah, I mean, I just want to make one comment regarding Python and R and the GSW library. That's probably one of the best examples where, even though they exist in R and Python, they use the same code underneath. They both use the same C library, which means that the science and the bug fixes for the actual TS10 happens on the C level. And every user, either R or Python, will get the benefit of that. And we need more of those, actually. The community, it's really hard to bring someone from Python to R and vice versa, because we are not programmers, we're scientists. We use what we learn. So when we have some hardcore piece of science like that, it's nice that we have a common language that we can all wrap and benefits. And in my opinion, the RGSW is a good, nice example of that. I am biased because I am the maintainer of both the Python and the C version.
Yeah, and I'm one of the co-developers for that R package, and I agree with Felipe that, you know, and he knows we are always going back and forth between the R and the Python fixes for that, because we both rely on the C, and actually it is a really nice system for being able to keep things consistent across analysis languages. Even when we don't use the same underlying library, like I always keep an eye on ROC, and Clark and I on my package Python CDT, and we make comments on each other packages to improve both packages every now and then. I actually made several notes that I'm going to implement on my package after this tutorial.
Well, I just love that as a facilitating reproducible science. That's awesome to be using common underlying libraries and multiple tools and consistency across all of this. Looks like there's one more question. Are there other oceanographic specific packages for R that you recommend or use together with OCE?
Yes. Yeah, there are a few. So the GSW one is obviously important. I'm just going to find, I'll go back to the rendered one, because there's some links here. I think I had a link for the CRAN. Hold on, where am I? I'm lost now. Anyway, what's the CRAN one? Here we go. If you look at the CRAN site for OCE, it shows, if that loads, hello. Anyway, it shows some of the packages that OCE suggests, right? So there's a lot of things that we don't require that you have, but there are ones that we suggest that you may want to use depending on what your needs are. Maybe the GitHub one will work. I'm not sure. No. All right, doesn't want to do that within the notebook. I'm just going to kill that for now anyway. But one that we use quite a lot is a package called MarMap. It's very good for doing bathymetry and making plots, getting bathymetry data, but also making plots for that. There are some packages for doing carbon system calculations, right? So CO2 system kinds of things. I'm blanking on other ones right now. Maybe Nick knows of some, actually, he could probably recommend, but you know, I'm like, actually, one of my criticisms of OCE, because I'm allowed to criticize my own package, is it's a little bit too big, actually. There's a lot of stuff in it that if I was going back a decade, we would say, no. The CGD stuff should be one package. The ADCP stuff should be another package. The mapping stuff should be another package. And they should all connect together, but they should be a little bit more modular. And I see Dewey Dunnington is on this too. And he's doesn't have his camera on, but I know he's sitting there nodding his head. So yeah, it's just a comment.
Fantastic. Well, I think we're at 15 after. It looks like there might be one more question about does it deal with flow through data, but I'll let you answer that maybe in the Slack channel, and
Yeah.
everybody can have a couple minutes for break. Looks like the break's from 15 to 30 after. I feel like that